Okay, so welcome to lesson 6 of your electricity unit of work, and this lesson is on resistors. So after you find the first page of this, as it will be shown in your booklets, have a look for me after you've read through the specification information at the knowledge check questions for me, please. You'll see they're all blanked out here. If you could just spend 5 minutes pausing your video and having a go reviewing your work from your previous lessons at these questions. Once you've done that, unpause the video and we will go through them. Right, so you should have unpaused the video and we'll go through the answers to the knowledge check questions. So mark them and correct them and green pen them as required. Symbol for potential difference is V. Unit for potential difference is volts. Identify the symbol for current, I. Name the unit for current. Amps, long version amperes, A, the symbol. Identify the symbol for resistance, R. Identify the unit for resistance, ohm. Identify the symbol for the unit of resistance, upside down horseshoe. For the same current, if the resistance is doubled, describe the change in potential difference. It's also doubled. The relationship is proportional, or directly proportional even. Right. On to the next page, and if we have a little bit of a look at the first paragraph. So there's some annotations and some notes I'd like to make as we go through. So if we start with this idea of an ohmic conductor. An ohmic conductor is any conductor which follows Ohm's laws. You can see that from the equation of Ohm's law, which is V equals IR, or in other words, voltage equals current times resistance. If we just change the highlight a little bit. Voltage equals current times resistance. And that's for a fixed value of resistance. And for a fixed value of resistance, the current is proportional to voltage. So, what we mean by that is if we just zoom out a little bit. If it's proportional, it means it corresponds in size and amount to something else. So the current corresponds in size to the voltage. Now, if you remember, resistance from last lesson is how hard it is for the charge to flow around a circuit, because the electrons that are carrying the charge collide with atoms and ions within the circuit, within components, within the wires. Now, Ohm's law can be stated as follows. The current through an ohmic conductor at a constant temperature is directly proportional to the potential difference across the resistor. So, in other words, as the current increases, so does the potential difference. That's the relationship between the two in an ohmic conductor. So this means that the resistance remains constant as the current changes. So you want to add those annotations into your own notes that you're making right now. Then if you have a look at this checkpoint question, pause the video and see if you can answer it for a moment. Right. Should have unpaused the video and see if you can answer the question, what is an ohmic conductor? State the conditions required for it. The answers are obviously in the paragraph above here, just to get you to review that. So an ohmic conductor is a conductor for which current and potential difference are directly proportional. And then that means the resistance remains constant as the current changes, and the temperature must be constant. So let's go through the second paragraph. Current potential difference graphs, or as you might see written, IV graphs. If current flows through a conductor, there is a heating effect. The electrons collide with the atoms as they pass through the resistance, causing the electrons to lose energy and the atoms to gain energy. So, if we think about this a little bit more directly. The electrons collide with the atoms as they pass through the resistance. So the atoms of the wires and the circuit components, the filament bulbs, the resistors, the light bulb, the variable resistors, the atoms that make them up. Now, they collide and it causes the flow of electrons to slow down, which means as they slow down, the atoms themselves of the components of the wire gain energy from the electrons. Now, the atoms vibrate more as they gain more energy. And if something vibrates more, the temperature of it increases. So as you know, if you touch a wire that's on, it gets hot. That's what's causing it. The electrons are bashing into it. Now, the resistance of some components is not constant. The combination allows circuits to be designed to control the current. An IV graph can show us how the resistance changes as current changes. So if you have a change in the potential difference, you can change the current, because as we said at the top, they are proportional. Now, for an ohmic conductor, resistance is constant at a constant temperature. Therefore, the IV graph is a straight line. Other components have different relationships. So if you have a look here, for a resistor that is fixed, it's an ohmic conductor, only has a set resistance, the relationship between current and voltage is directly proportional. As one increases, so does the other. The relationship is linear. If you can remember, that is the whatever it is, symbol. There you go, the symbol for a resistor. Whereas moving on, as it said, the relationship for other components are slightly different. So for a filament lamp, symbol there to remind you, it's a non-linear relationship. The voltage increases, more force shoving the electrons around the circuit. As that happens, the filament inside the light bulb heats and vibrates. So if you remember when you've got a light bulb, it's going to be a terrible drawing, you've got the kind of little wiry bit in the middle, like so. As the electrons move around that, this heats up and vibrates more, which increases the resistance. It makes it harder for the electrons to go round that filament wire, which means current becomes less and so starts to taper off as the voltage is increased quite rapidly compared to where it started. And then finally, for a diode only allows current to flow in one direction. So here on the graph, voltage is increasing, but the current is 0. Because the current is flowing in the wrong direction. Whereas when it starts to move into the right direction, it then increases in a sort of almost directly proportional relationship, just like a fixed resistor. But down here, where it's 0, the resistance is incredibly high. So therefore, that stops the flow of current. So it stops the flow of current in the wrong direction. So, gone through that, but if you needed to pause the video at any point or to go back and just make sure you've got those annotations down on your graphs, make sure you do that before we now move on. Right. So, as just says, this summarizes the relationships that we've been talking about. So, in a filament lamp, the resistance increases as the temperature of the filament increases. So, there's less current because increase in resistance makes it harder for electrons to flow. Then, current through a diode only flows in one direction, and the diode has a very high resistance in the other direction, which means can't have current flowing. There's no current flowing. Now, a thermistor, thermal resistor, the resistance changes according to a change in temperature. So the resistance of a thermistor decreases as the temperature increases, which means it's easier for the current to flow through a circuit that has a thermistor in it if the temperature gets hotter. Now these might be used in things to control thermostat in an electric kettle, for example. Then an LDR, a light-dependent resistor, the resistance of it decreases, the light intensity increases. So it's easier for the current to flow as the light intensity increases. So these might be used for things like turning on street lights or automatic lights when it gets dark. Right, you've gone through that. Now again, pause the video and just see if from memory you can answer this checkpoint question using information we've gone over. Right, unpause the video and you'll see your answers there. Lamps, diodes, thermistors, and light-dependent resistors. Right, okay. Just see what we've got. Reminding myself what we've got there. Right. Let's have a little look at this. Now, so, where we might have a practical that you could do in class, you'll be able to, but here we obviously can't do it in class, so we're going to walk through it step by step. So, investigating components. Resistance is affected by both current and potential difference. We know this because of the equals IR relationship. So you've got two following circuits. Now, from V equals IR, we can also make R the subject of the equation. So we can know that resistance equals voltage divided by current. Now, if we're going to, therefore we need to measure the current and the potential difference across the resistor to see what it is. So the variable resistor, now we know a variable resistor, you can change the resistance applied to the current, can control the current and give a range of values for potential difference in currents. So by doing this, we can check if the resistance remains constant as the current changes, which would make it an ohmic conductor. The ammeter measures the current, while the voltmeter measures the potential difference. Remember your symbols. The power is supplied by the battery. Have a look at the table below. So, if we were to take a set of data like this, and we were to say, okay, we've got current, 0.89 amps, voltage of 9 amps, and current of 0.44 amps and a voltage of 9 amps, what would the resistance be? Voltage divided by current. So if you did 9 divided by 0.89, find the answer, and you'll see that it's about 10.11. Same again, 0.44 divided by 9. Sorry, wrong way around. 9 divided by 0.44 is 20.45. So what we know here is that in this circuit, if we've calculated current as 0. And the voltage, we've worked out the resistance of the resistors, which we know resistors might come in 10 and 20 ohms. Right. A little bit of practice time for you. Pause the video. Have a go at this question for me, please. Use any of your own resources, notes that you've gone through so far. Right, unpause the video if you've had a go at that, and you'll then see that the answers are on the side over here. Pause the video. Have a look at your answers. Have a look at what's here. If there's anything that you're unsure about, make a note of it. Make sure you email your teacher about it. And then another set of questions to have a little look at. Pause the video. Which of these can you do? What information do you need from your notes, from any extra resources? Right, hopefully you've had a little go at those. Unpause the video and then have a look at the answers. Pause the video, go through your work, go through your answers, see if anything matches. If anything doesn't, make a note of it, email your teacher about it. Right, and then move on. Right, so we've said about LDRs, light-dependent resistors. So, as you've got more light, you've got a low resistance, which means you've got a larger flow of current. So light intensity of 7, resistance is lower, isn't it? Whereas light intensity of 0.5, low, which is dim light, got a high resistance, so it's high resistance in the dark. So the key thing to remember when it comes to LDRs is the more light, the lower the resistance, the more current. So, pause the video now and plot that data as a graph for me and draw a line of best fit with it. Right, should have had a go at drawing a graph for me with a line of best fit, and you will see that you've got a general trend that goes down like that in the shape of your graph. And it's just remembering that this shape of your graph shows that relationship for an LDR between resistance and light intensity. Right, have a go at these questions for me now. Pause the video, have a go at these questions based on what you've looked at. So how does the resistance change as the light gets brighter? Mark these as you go, correct them if you need. The resistance decreases. How does the resistance change as the light gets dimmer? Opposite, the resistance increases. What's the value of the resistance when the light intensity is 3.5 units? So find 3.5 units on your graph, read up and read off the value of resistance. If you've plotted it correctly, you should find that it's around 35,000 ohms. And again, what light intensity will give you a resistance of 50,000 ohms? So find 50,000 ohms on your graph, then read across and down to light intensity. What value do you get? Hopefully about 2.5 units of light intensity. Right. Again, similar idea. For a thermistor, so a thermistor, if you remember, thermal resistor. So draw a rough graph to show resistance against temperature. And if you look at this, remember, if you've got high temperature, you've got low resistance. Low temperature, high resistance. So if you've got high temperature and low resistance, it means the current is going to flow more easily. Good. Okay, so same thing. Pause the video, plot a graph of that data. Right, if you've done that and unpause the video, you should now see, you should have a general trend in terms of you start with a high resistance, and as the resistance decreases, temperature increases. So again, so you should have a relationship similar to that with an LDR, if you've plotted it correctly. So then, again, go to these questions, pause your video, have a go at these for me, using your graph. Right, unpause the video. How does resistance change as the temperature gets higher? It decreases. As temperature gets lower, it increases, the opposite. Again, read the values off the graph. So the value of the resistance when the temperature is 75 degrees. Find 75 degrees on the x-axis, read up and across to the value of the resistance. You should find it's around 75. Temperature, when you've got resistance of 160 ohms, reading across to your line of best fit and back down again. So just remember, what we're talking about is we're reading across and down when we're trying to find values on our graph. What temperature will give you a resistance of 160 ohms? About 15 degrees Celsius. Right, now that you've had a go at that, pause the video and see if you can have a go at these two questions using your own notes, using any internet resources, using the information from this lesson. Once you've unpaused that, once you've unpaused that and had a go, I'll show the answers. Right, so hopefully you've had a go at these, having paused the video. Let's now show the answers to them. Oh, no, wrong one, sorry. Answers are over here even. So these are your answers for these questions. Mark them as you see fit, please. Again, if there's any questions in there you're not sure of, you haven't understood, you don't understand why that's the answer, make a note of them, put them in your email, put them in an email to your teacher. Right, second activity that I'd like to have a go at then. How many of these knowledge recall questions can you answer? Pause the video. Separate sheet of paper, a notes page, something like that. How many of them can you have a go at? Doesn't matter if you can't do all of them. See how many of them you can do. Right, if you've had a go at these and you've unpaused the video, you've then got a final activity to be done, which is your knowledge check questions. So, finally, review your content, have a look back over your notes, see which of these just jump out at you, pause the video, have a go at the questions, and then mark your answers against the answers that I give you. Right, you should have had a go. So if you've unpaused the video, here are your answers. There are your symbols for each of those. Non-ohmic conductor. Remember, with a non-ohmic conductor, the relationship between voltage and current is not directly proportional. So an ohmic conductor might be a fixed resistor, whereas these aren't. So resistance for thermistor changes with temperature decreases as temperature increases. Resistance for an LDR changes with light intensity. Resistance decreases, light intensity increases. Don't forget, these can also be written in the opposite manner. As the temperature decreases, resistance would increase. As light intensity decreases, the resistance would increase. We've mentioned about uses for LDRs, lighting circuits in street lights, automatic lights, and just remind you about magnetism if you've ever done that before. Just jogging your memory on magnetism. Repels and repels. Good. Then as you see, there's a final activity. Suggest why the known value of resistance and the measured value above may be different. Now, pause the video, have a think about how, or what impact even, heating effect might have. So, the heating effect can mean that the results of an actual experiment can differ or deviate from known values. And they can also differ due to human error as well, okay? So just a little extra activity for you there. So, that's our lesson on resistors. If there was anything you didn't understand, weren't sure, watch and review these videos that will be in the description underneath, and just make any notes that you want on your student notes page. And this contains all key information about the relationships in terms of resistors and resistance in each of these different circuit components that you need to know about. But otherwise, that is your lesson